All right, so one very interesting trend that has been observed for many decades in transition metal chemistry has been ligand substitution reactions of square planar complexes that have a significant uh, effect on their reaction rates depending upon what ligand is trans to the ligand that you're doing the substitution at. Okay, this is called a trans effect. And so another way of saying that is the nature of the ligand trans to the ligand substitution site heavily influences the reaction rate. This is common in square planar complexes. Okay, and so empirically, what people knew for a long time before they knew the origin of this effect was that it followed this trend with ligands. So if you had like carbon monoxide or an ethylene ligand, those trans to your ligand substitution site, those reactions occurred very fast. But if you had like fluoride or hydroxide or water, those were very slow. And so it followed this empirical trend, and it didn't really matter what the metal center was, as long as the metal center was the same between the two complexes you were comparing. It would always follow most of the time this empirical trend. And so this trans effect, we're going to talk about where it comes from in a second, but it's useful in synthesis. So we talked about cisplatin earlier in chapter 5. And so this kind of will illustrate, how the trans effect plays a role in synthesis, in the synthesis of cisplatin. So let's say cisplatin, remember, is an important anti-cancer drug. So let's say you start out with this tetrachloroplatinum anion, and then you react it with ammonia. And if you react it, with one equivalent of ammonia, you will get, well, one of the ammonias substituting the chloride. So that's not very exciting. That's kind of all can happen if you only let one equivalent react. But then when you react a second ligand, you have a choice whether or not to make the cis or the trans isomer. And the trans effect tells you that you will make the cis isomer. Okay? And why is that? Let's look at that. What is the option? If you make this cis isomer, right, the ammonias are cis to one another and the chlorines are cis to one another, they're next to one another. That means you're doing substitution at this chlorine, okay? Well, what is trans of that chlorine? It's another chlorine, okay? Now, if you were to make the trans isomer, if you needed to make the trans isomer that had a chlorine here and ammonia here, okay, in order to do that, you would have to substitute this chlorine. And what's trans to this chlorine? Ammonia. So the question is, what has a greater trans effect? Ammonia or chlorine? If we look, chlorine has a greater trans effect. So we know the rate of the reaction, trans to chlorine, is going to be faster. And so that is why we get a cis complex. Because if we're trans to a chlorine, well, this chlorine is trans to a chlorine, so we could substitute that one. That would be ammonia. Or this chlorine is that would be cis, right? That would be ammonia, be cis, make a cis like this. Or this chlorine is trans to this chlorine. So if this got substituted, it would become ammonia and become also cis, just this rotating 90 degrees. But if we try to do substitution on this chlorine is trans to ammonia, so that one is not going to be as favorable. And that was what would make the trans isomer. Okay, now look at if you start with an amine complex, okay? So with 4 ammonia ligands, what would happen? And now instead of doing ligand substitution with ammonia, we're going to do ligand substitution with chlorine. All right. So now you're going to make the monosubstitute product, nothing interesting. And now what's going to go faster? Well, the trans effect tells us it's going to be the one trans to chlorine versus the ones trans to ammonia. So the one trans to chlorine is this ammonia. So if you substitute that out, you're going to end up with trans substitution in your final product. So just by doing very similar chemistry, right, kind of a different order of the reactions, you could distinguish between making the trans isomer, okay, and the cis isomer. Cisplatin, this one, is the only one that has anti-cancer activity. So it's a big difference, in some cases. All right, so where does this trans effect come from? The trans effect is the influence in the observed rate constant. So that's what we've been talking about here and here. Okay. The trans effect has two origins. One of these origins is called the trans influence. And the trans influence is a change in ground state due to trans ligands. And so if you have a big trans influence, okay, you will have a difference actually in the bond strengths and bonds lengths, okay? That is called the trans influence. And so this trans influence comes from the fact that if you have a strong sigma donating ligand, okay, those tend to weaken bonds trans to them, okay? So if this X1 is a very strong donating ligand, sigma donating ligand, this bond is going to be relatively weak. That's why I drew it longer. Why is it going to be relatively weak? Because ligands trans to one another tend to use the same orbitals for bonding. So they're competing over the same orbitals for bonding. So if one's really strong, the other one has to be weaker. Stronger sigma donor ligands, therefore, have stronger trans influence. Okay. The other thing that's going on here, so you can see these in like the ground state crystal structures, all right? The other thing that's going on here is a transition state effect, okay? So these two things, the trans influence and the transition state effect together give rise to the trans effect. The transition state effect is this effect that stronger p accepting ligands pull electron density away from the metal, which allows incoming Lewis bases to be more nucleophilic, okay? And so if you have a stronger pi accepting ligand, I should say pi accepting ligand, then that is pulling electron density away from the metal, okay? Because think about this here. So if you have two ligands and they're trans from one another, and now you have electron density going into here, well, we already established that these electrons use a lot of the same orbitals when they're in this trans configuration. And so if you have electron density pulling away, well, that's going to make it easier, right, to do substitution here at the trans ligand because it's just more vulnerable. The metal is more vulnerable. You can remove electron density away from it, right? So it's basically, in some sense, a stronger Lewis acid from the perspective of the Lewis base. So together, the trans effect, this kinetic observation, is a result of the trans influence and this transition state effect. So as a result, the strongest trans effect are strong sigma donators and strong pi acceptors. Pi acceptors from the transition state effect are good from a transition state effect perspective, and sigma donators are good from a trans influence effect. So if you go back and you look at this list, this trans ordering, you know, things like CO and ethylene, those are strong pi acceptors and also pretty good sigma donors. Something like fluoride can't do any pi accepting, okay, pretty much, and it's a pretty weak sigma donor as well. All right, so that is the trans effect.